Hello, and welcome to All Space Considered, everyone. My name is Dr. David Reitzel, and All Space Considered happens on the third Thursday of every month, and it is brought to you by Griffith Observatory, the Department of Recreation and Parks of the City of Los Angeles, and as always, we like to thank Griffith Observatory Foundation, our exclusive nonprofit partner for so much of what we do. Tonight with me on the panel, or my co-host, is Laura May Abron, and we also have Bill Gruneberg and Jared Head with us tonight. Ginger couldn't be with us, unfortunately, tonight, but we look forward to having her back next month. Well, first of all, it is the third Thursday of the month, and today is May 21st, 2026. It's about the latest our show can ever happen on the 21st. Tonight, we've got a really great show for you. We're going to have some space news to kick off the show. Psyche spots a red planet. Soccer balls in space, although that one I think we removed because Ginger was going to do that one. Right. So we're going to let her present that now when she returns. And then we have an atmosphere least expected, a star party for the ages. The Mostest makes its appearance. Jared will cover Out to Launch for us. And a how-to guide, aurora-chasing. If you've ever wanted to go see the aurora borealis, or if you're crazy, the aurora australis, but we'll see if we recommend that. But we're going to tell you about that. And then Spherex maps glaciers in space. And then finally, we have a few astronomical images, but again, Ginger covers that, so it'll be very truncated, just a few cool things that happen around the observatory. And then we're going to end with another short segment of Astronomy Beyond the Visible, about how astronomers are using multi-wavelengths and even some things that are not light to study the universe. So that's our show tonight. So let's kick it off and talk about this image that's behind our title there. This is an image of the Sombrero Galaxy, Messier 104. It's nicknamed the Sombrero Galaxy because in some amateur photographs it looks like a lot like the famous Mexican hat. It's a popular target for amateur observing. You can see it through a moderately large telescope. A 20-inch, you can certainly see it pretty well. You can make out that dust lane that's in the middle. This image is amazing because it clearly shows that disk of material, the dust lane crossing it. But not only that, that huge halo of stars, that glowing white light, are stars in the outer regions of the galaxy, and also about 2,000 globular clusters that each have hundreds of thousands of stars in them. Another thing to note is that arc in the lower right, the lower portion of it, there's sort of a sweeping loop. That is a dwarf galaxy that fell in and was shredded by the tidal forces of the Sombrero Galaxy as it fell in. This is how galaxies grow. They eat other galaxies. So very cool image. I could go on for a long time, but we've got a show, everybody. So let's get on to some space news. And tonight, we're going to kick it off with a story about Psyche. The Psyche mission was launched on October 13th, 2023, and it's headed out to the asteroid Psyche. It's a metal asteroid. I mean, it's made of iron and nickel, and we'll learn more about it when we get there. We'll find out how much rock is there. But we know it's made of metal because it's incredibly dense. The density of it is very high. And it'll reach there in late July 2029. But on the way there, it passed by Mars just recently. In fact, it passed by May 15th at about 5:03 a.m. our time. And they took some pictures. This is a beautiful picture of the crescent Mars. The sun is kind of behind, just a picture you wouldn't normally see of Mars. People aren't used to seeing that. Since it's external to our orbit, we see it generally fully lit. So this is a cool view of Mars you don't normally get. It did get some high-resolution photos where it tested the equipment that's on board. This is the multispectral imager instrument, and it's enhanced color. They've boosted the colors to bring out the chemical differences. Upper right is the Huygens crater, which is about 470 kilometers in diameter, about a little under 300 miles if you roll that way. And the surrounding heavily cratered southern highlands are shown off in this. Another picture it's the Martian surface that's showing streaks that are caused by the wind. The wind is blowing that dust, and those streaks are about 30 miles long. And the large craters near the bottom of the scene, you can see are interacting with that dust. And just again, a beautiful image that's proving that the spacecraft is healthy and the scientific instruments are working well. And another image it took is this really cool one, looking down into the southern part of Mars. That's the southern polar cap. Yes, Mars has polar caps. It has water ice in the polar caps and also carbon dioxide ice that comes and goes with the seasons. So totally cool view of Mars, and I'm really excited about the Psyche mission to get to Psyche and do its work. Well, this is a beautiful image of a planetary nebula taken by the James Webb Space Telescope MIRI instrument. And it's just a beautiful shot. This is actually part of the buckyball story that Ginger was going to tell, and I wanted to keep this in here just to show the beautiful image. This is sort of the birthplace of these complex carbon molecules that have 60 of them in there, and they build a sphere out of it. So tune in next month, and Ginger will tell us that story and tell us what this is all about. Well, Bill, you found a cool story about a trans-Neptunian object that we learned something about. What's going on with this one?
Well, it's a trans-Neptunian object. That means that it has this big elliptical orbit where, oh, am I not on?
Oh, yeah, you gotta unmute.
Oh, yeah. Oh, yeah. Okay.
And we're out of time. So yeah, this is an object in a trans-Neptunian orbit, which means it goes way out into space, big elliptical orbit, then comes back into the solar system, shoots through where Neptune orbits, goes around the sun, and comes back again. Pluto is one of these also. And this is a picture of, and by the way, did it go ahead of me for some reason? It's probably on a timer. Okay, so it also has an atmosphere, and it should not have that atmosphere. And I'll explain why. If I can read the elliptical orbit. Takes us, okay. I'm sorry, this is a little small for me. Okay. All right, so, okay, so some...
well, let's just compare its size to Earth and Pluto. Let's go forward and compare here. So you can see Earth and Pluto are that small, and this thing is that much smaller than Pluto, so it's tiny. It's only about 500 kilometers across, so it's a very, very small object. And this is the movie that you want to show, Bill, that tells how they made this measurement. And you can see here, the object is moving along, and as the star passes behind the object, this is called an occultation. This object from our point of view passed in front of a star, and the starlight was blocked out slowly. It didn't wink out immediately. You'll watch it return here. It brightens up slowly again. So it came into view, it brightened over time, and that tells us there's something fuzzy around this object. Now, why shouldn't this have an atmosphere, Bill? What do we think? What could possibly have created this?
Well, the big answer is we don't know. But what we think, or what scientists think, is that it could be something like some sort of heat generated from inside, kind of like geothermal energy, which might take some of this ice and cause it to sublimate, which ice does in space, which means it doesn't go through a liquid phase, it goes right to a gaseous phase, and then becomes atmosphere. The other possibility is that a giant comet, which again is a big hunk of ice, smashed into it at some point in the last probably 1,000 years. And I say that because any atmosphere on this tiny object should not last longer than 1,000 years, or Earth years, that is. So it could also be that. That's the other big explanation.
So super interesting thing that's going on, but this is the plot I wanted to get to, and I think I didn't tell you that I'd put this in here, by the way. That
a little similar to exoplanets. In fact, when we see a transit of an exoplanet, depending on the size of that dip or the orientation of that dip, you can tell whether that planet has an atmosphere or not sometimes. Yeah. So that's kind of an interesting...
So essentially the atmosphere would freeze out to the surface?
It should freeze out. Yeah. It should fall onto the surface and hang out there and slowly be weathered by space. But this is a really odd thing for one of these small, about 500 kilometers across, tiny object. It shouldn't have an atmosphere. The atmosphere that shouldn't be there. Yeah. So. Yeah. Well, Laura May, we had a cool star party recently.
We did. So it was the centennial star party of the LA Astronomical Society on the front lawn of Griffith Observatory. Let's give a clap for 100 years.
Yay.
Woo! 100 years.
We're halfway there.
We're halfway there. 100 years of public astronomy. Keep in mind, this is a lot of people who go into schools, who loan their equipment and their telescopes. And so we had organized this humongous party, and with the aim to bring 100 telescopes on the lawn of Griffith Observatory. Of course, these parties happen every single month, but this was a very special one with some talks. of course, as tends to happen for anyone who knows, I don't know who bought a telescope, by the way, the night before, but we had rain that day, of course, classic. And guess what? People still showed up. This is the dedication of the LA Astronomical Society. So you can see the booths. We had some images out to show also how long these star parties have been going on. All of these, I think it's many, many decades, 50, maybe 70 years, perhaps longer. The LA Astronomical Society is a little older than Griffith Observatory by 9 years. And just look at these people. Everyone covered their telescopes in trash bags, basically. Normally people would stay at home, but this was a unique centennial experience. And it was the return of a famous telescope that used to come very frequently to Griffith Observatory, the Velvoscope. So here is the owner, Jeff. That telescope is actually harnessed or attached to the roof of that car. In fact, one of the telescopes we have upstairs in the Zeiss Dome also came from someone who had it on a car. Was this popular some decades ago? When you have a large equipment, a large telescope, this is how you can actually move it, is you put it on top of your car. So it was pretty exciting. It looked a little like a cannon.
It does a little bit.
That's a good way to get parking up here.
That's a good way to get parking up here. And so it even featured in the Griffith Observer some time ago, our review. And this is a very famous Alvin Clark telescope. Now, the Alvin Clark, they created some of the largest refracting telescopes in the 19th and 20th century. And here is a homemade telescope that was made for the occasion of the 100th, a very unique piece. And the plaque that was actually gifted to us, to the LA Astronomical Society by Griffith Observatory. And to celebrate these 100 years, we now have this beautiful bronze plaque. You can actually go see it upstairs, technically the newest exhibit. Hanging in the, I think, Wilder Hall, I believe, of VI. I believe it is up there. So you will have to come back for a star party that is not raining in the coming months. But if you'd like to go to some star parties, there are, of course, many star parties nearby. But get this, how about experiencing the largest, biggest star party possibly in the world? And it happens next month at the Grand Canyon. It is their 36th star party from June 6th to the 13th. 8 nights in a row of telescopes, talks, all sorts of events. It's pretty exciting. It's such a monumental event. And it's only about 8 hours drive from here. And most importantly, they have reached about 95% compliance to the Dark Sky International. So I would say it's probably going to be your best bet to see the Milky Way close to LA. So I highly encourage you to head on over to the Grand Canyon for this star party. Very, very exciting times.
Well, just fantastic. Well, here is our MOSTest picture for tonight. Tonight we have a MOSTest that was the longest radio burst that the sun has ever done. In August 2025, originating from this feature on the sun called a helmet streamer that looks like this. This was taken during a total solar eclipse in 2017, but you can see this sort of V-shaped streamer coming off the sun on the right-hand side. And when those happen, you can also get radio bursts. They're not sure how these are all connected, but sure enough, the sun started to burst in radio waves, and it went on and on. Normally these last a few hours, maybe a couple of days. This radio burst lasted 19 days.
Wow.
19 days long. The previous record was only 5. So this blew the record out of the water. This is completely new and totally a new MOSTest. Wow. So the sun set a new record in 2025, and the paper came out just recently where they put all the data together and recorded it and said, it didn't stop for 19 days. So very cool result for our MOSTest.
Wow. Well, congrats to the sun.
Congrats to the sun.
Yeah, exactly.
Great job, son.
Absolutely. Well, it is time for Out to Launch with Jared.
Yes.
So, Jared, what do you got for us tonight?
So first off, I wanted to take us back to last month for Artemis 2. Woo-hoo! I'm sure we all, who paid attention to Artemis 2 in here? Because, oh my gosh, I could not sleep for like 10 days. I was glued to my computer and TV watching it. So we've been starting to get footage, really high quality footage coming back. So what I'm about to show you, this upcoming video is actually separation of the Orion capsule from the European service module. And the audio is real in this because the vibrations from the explosive bolts and the systems in the service module are being sent through the material that the spacecraft is made out of and into the GoPros that are on the end of the solar arrays, because they used GoPros for it. Yeah, they used GoPros. Can you believe it? So check this out and listen to this.
I thought in space nobody could hear you separate from your
Yeah, well,
from
turns
your
out
modules.
it's a thunk. It's a big
a
thunk.
It's a little champagne cork.
And you can see that that's a connector that connects the European service module systems to the Orion capsule, and we're 10 minutes away from re-entry. So
I love the wobble that occurs in the solar panels, that's
Yeah.
shaking the camera.
yeah, it's a little it's got some oomph behind it there. So.
I was surprised to learn that when they work out, it makes the entire module rock.
Yes. So they actually have to schedule the times for the astronauts to work out, so that way they don't, over vibrate the solar panels on the spacecraft.
Okay.
So it's pretty wild. So it turns out not everybody's hitting the gym at the same time in the Orion capsule. So if you go up there, pace yourselves. We also had a launch from Blue Origin earlier this month as well. Their New Glenn rocket, which is now one of the largest operational rockets in the world. This was its third flight. And the whole goal of Blue Origin is very similar to SpaceX's, which is to have reusable rockets. So they have their own lander out in the middle of the ocean. And as SpaceX has Elon Musk, Blue Origin has Jeff Bezos throwing the money into this here. But this rocket is over 300 feet tall. It's absolutely gigantic. Wow. It's almost 4 million pounds of thrust off of the pad. And it's methyl oxide. It's using liquid methane and liquid oxygen in order to fly.
Is that what makes the color?
Yeah, the mythical blue flame.
Okay.
It's not just something here on Earth. It's also something you can get out of your rockets now as well. Now, this was carrying a communications satellite that was going to be going into medium Earth orbit, but unfortunately, there was a problem with the upper stage. The engines took it to orbit, but they did not restart to put the communication satellite in the correct orbit. So unfortunately, that satellite was a total loss for that company. So we'll kind of have to see if that company gets their insurance money for it or not. No joke, there is actual insurance that companies will pay for that just in case.
Now, is this going to re-enter? Are we going to see video of
Yes.
it? Okay.
So here's the upper stage engines as they're about to turn on. So they separate to give themselves a little bit of room, and then they'll turn on, and you'll actually see these sort of ribs fall off of the engine. Those are stiffeners, so that's perfectly fine for those to come off of the engines. That's expected of them. But here's the first stage returning. This first stage, by the way, its name is Never Tell Me the Odds. So,
never tell me.
Never tell me the odds. It's coming down to the ship it's going to land on, called Jacqueline, which was the name of Jeff Bezos' mother. And we can see it coming down. And this first stage is actually the size of an entire Falcon 9. And you can see it kind of does something a little different. The Falcon 9s from SpaceX, they do what we like to call a hover slam, where they hit zero right at the ground. But this one, this smooth operator, all on its way into landing right at the center of that there. So this flew the second mission last year in November, and now it's flown again. So this is essentially a reusable and proven reusable rocket system. So now SpaceX is probably going to have competition for their Falcon 9 as soon as Blue Origin can get their New Glenn rocket flying more often. So we'll have to see. The future is the competition between those two, it would appear.
Is there an advantage to those different ways that they are re-landing the boosters? So
it really depends upon how much you want to lift and your technique. So SpaceX is maximizing their throw with the Falcon 9. So the whole goal of that is to use as little as possible So you're going to use more atmosphere to slow yourself down, and then you're going to really time it just perfectly so that you land and you expend the least amount of energy that you
slam
can.
that you were saying,
so that hover slam, and you know the legs on the Falcon 9s have crush cores in them. So if they do land too hard, they can crush the core inside of the leg, and then they just basically remove a leg, put a new leg back on it. But you could see on the New Glenn there, the legs were a bit smaller, a bit skinnier. So it's all about landing nice and gently and maximizing that. Also, New Glenn is massive compared to a Falcon 9. It's 100 feet taller, and the diameter is almost twice the size of a Falcon 9. So it's chunky boy. It's an absolute unit of a rocket compared to a Falcon 9. So it can do something like that with a payload that a Falcon 9 would need to hover slam with. But we do want to talk about SpaceX, and they did put out a documentary recently called Test Like You Fly, and we got to see some things with their Starship program. Like we got to see the cryogenic test that happened last June, and or the static fire that didn't exactly work out so well. We'll see what happens.
Oh, yeah.
That's not a good result.
Yeah, that's suboptimal. So there's what was left over of ship 36, and then also this is what happened. They blew up the ship and they blew up their test site as well. And this is the first time we've really had like up close imagery of that. And then Booster 18, which was supposed to do Starship Flight 12, that one unzipped itself back in November. So here's what that looked like up close. So it's interesting that we get to actually see these failures coming from video from SpaceX themselves.
Oh, no.
So that's also bad as well. You don't want to be popping your boosters like that. You want to be popping bottles once you've flown really well, but popping boosters in spacecraft, not so good with that. But we were all hunkered down, and we were here today at the observatory getting ready to just do like a full-blown news blitz and do editing, because Flight 12 of Starship is happening today. It's the first ever version 3. They basically went back to version 2, which was giving them tons of problems, did a near clean sheet design. Basically, really the only thing carrying over was the engines, and even those have been uprated as well, and they got everything set. They were ready to go. They were 40 seconds from launch, and then they had a hold. But they said, okay, we're going to recycle the count, so we're going to go for it again. And they got into it, and they were about 10 seconds away from launching, and they went into another hold. And then they said, okay, we're going to try to work to recycle the count. We're going to do this. Okay, we're not flying today. So unfortunately, we were not able to get you some spectacular footage.
Was it a boat out on the ocean too close? Or
from what I saw, it was actually a pin to help retract a hydraulic arm.
Oh, one of the remove before flight.
It could be a remove before flight for all I know. But yeah, so we'll see. We'll see if they can fix that overnight to fly tomorrow or in the next couple of days. But I'm very sorry that we didn't get to show you awesome footage of the world's largest rocket flying to a suborbital trajectory. But next month. We'll see you in June for that. And that is our out to launch for May.
Thank you, Jared. Appreciate that.
Yeah.
Really terrific. Yeah. Well, now it is time for your guide to aurora chasing. Laura May,
I'm getting
warm.
ready,
You're getting ready
to
go
prepare
chasing?
all of you to come with us on this guide
Okay.
to aurora chasing. So who here, show of hands, who here has seen the auroras? Okay, a couple people.
Okay, a few people, yeah.
Who here has wanted to see the auroras? Yeah? If your hand's not up, I'm going to have
If
some
your hand's not up,
for you.
Well.
So I've been chasing for about 15 years, and so we've put together, several of us, Bill, in fact, also chased this year. Ginger, who can't be here, chased for the first time this year with me. And we've put together this little guide to help you understand a little bit of what's going on with these aurora and to help you potentially find them. So the first and most important thing is that they are related to our favorite object, of course, the sun, right? You'll notice on this, this is a visible light image of the sun, by the way. So you are seeing the actual color of the sun, and all those little dark regions there are sunspots or active regions. They will occasionally emit a flare, little solar eruption, and from that eruption, we sometimes get the ejection of material, seen right here. This is what we call CME, so a coronal mass ejection. And you can see here, it's actually aimed away from us. It is going further out into the solar system, potentially hitting another planet that might be in the way. And right here, what we have is a halo CME. And so you can see it is going straight for us and going all around us. And that little dot right there on the side, that is most likely planet Mercury. And you're looking at billions of tons of magnetized material or plasma that are ejected from the sun and ejected from space. So the sun is right in the center of that image. We have to hide it with what we call coronagraphs in order to see all of that emission around it. So how does it happen? Once it leaves the sun, it is out in space, it interacts with what we call the interplanetary magnetic field, and it eventually, if it is aimed towards us, a lot of them miss us, but it can interact with our magnetic field that protects the Earth, of course, and this is how it happens. So some of these particles, all of these charged particles from the sun, they're going to travel along magnetic field lines, and occasionally that will cause this magnetic reconnection. This is a snapback, kind of like a rubber band, and all of those electrons are being kind of pushed down all of these magnetic field lines, and you can see they are traveling all the way to the poles and being funneled down where they create the aurora. You have some interactions in our very, very high up upper atmosphere that will create them. Now, you might have noticed that there are different colors visible in the aurora. You've got green, you've got red, and how common are all these different colors? Why do we have these different colors? And what can you actually expect if you go see them? Now, it is true that most of the colors you are going to see are going to be green most of the time. That is overwhelmingly the color of the aurora, but occasionally you can also see some red. When we've got much higher up, we've got interactions with oxygen. So these little interactions release a photon, and then we've got these beautiful colors. And lower in the atmosphere, occasionally you have the blue aurora. This is a real picture. They don't appear very often. I've never seen them. Some friends of mine have seen them. And these are caused by interactions with molecular nitrogen ions. And they often occur, these blue auroras, when you've had a very, very big, very active geomagnetic storm. And that will be sometimes at the end of the night, you will get this residual little aurora when there's a lot of depletion in the atmosphere. So an exciting one to look out for. Now, where do they actually take place? Well, if you were paying attention, you've probably noticed that we talked about the poles, right? So this whole region you see in green there, we call this the auroral oval. And you can see it circling the polar region. It appears to circle the North Pole, but in reality, it is circling the magnetic pole. So right here, that cross, that is where it is right now. It's headed towards Siberia because it does wander, right? Our magnetic field is created by our liquid iron core. And so that magnetic field, the pole of it is wandering a little bit. You can check out the maps, and it wanders pretty quickly. Every year it changes, which is pretty exciting. Mm-hmm. So the Earth is rotating under that auroral oval. And you might be wondering, we talked about the northern lights. Are there southern lights? There are indeed southern lights. As you can see on this image, though, they are centered largely over Antarctica, so much fewer people living there, much harder to reach, and not the greatest place. Occasionally they are seen from the southern coast of Australia, southern coast of New Zealand. Unfortunately, penguins, they don't have opposable thumbs yet. Maybe someday we'll give them smartphones and they can take great images of the lights.
We have a museum guide that goes down to Murdo.
That's right,
and cooks down there, does amazing work. Maybe we can see if James can get some photographs of aurora from the south.
And Bill, you went on your first chase this year. Very exciting.
Yeah.
Where did you go?
We went to Fairbanks, Alaska.
Right there.
Yeah.
And why did you pick Fairbanks, Alaska?
Well, because my wife chose it. She's a great researcher, but we looked at it together, and it was price-wise, it was fairly affordable. It was not having to go halfway around the world, and it turned out to be a great location. All right. Well, this is the.
This is part of why it's a great location, right?
Yeah. Although we didn't go in there, that's the. I'm forgetting what that's called. The
hot springs.
Hot springs.
Hot
yes.
springs,
The hot springs. And nobody actually was in there when we got there. We had a nice lunch. That's what I recall.
That's,
Yeah.
you know,
Came back home.
and there is a #1 ingredient that you do need when you are aurora chasing cooperative weather, right?
Yeah.
Did you have good weather?
We had great weather. Yeah.
That's
well,
very
with
fortunate.
an exception. The first 2 nights were quite good. The second night was even better than the first night where we went. And we had a nice dark sky. The third night we heard was going to be amazing. I mean, like so much solar activity, so much stuff hitting, our magnetosphere. And then we had clouds. We had like thick clouds all night long, so we weren't able to see a thing of that, and that was a little disappointing. But I was not unhappy because we did see. You'll see I've got some pictures in here, and we had a couple of good nights.
And I generally recommend people stay for several nights. Don't just go for 2-3 nights and expect to see them.
Right.
Stay a week if you can. Stay 5 days to maximize your chances of having good weather. Now this is the lodge.
Just the lodge. It didn't look like that because it was incredibly dark. We were bumping into each other because we wanted to preserve our night vision. But there are 2 things that I liked about this. By the way, this is called the Aurora Borealis Lodge. Very easy to remember. And there's a gentleman by the name of Moke who runs it, and he's fantastic. I would recommend this place, but go wherever you feel like you want to go. Those windows are there so that you can actually be checking to see if aurora are starting to come back. But in the meantime, on the left there, you can see there's hot coffee, there's hot water for chocolate, there's hot tea, there's hot everything, and I was pounding hot coffee not only to stay warm, which was very difficult to do up there, but also just to stay awake till 2 or 3 in the morning.
Yeah.
Cookies too.
It's important.
So it was a nice little.
I'm
it was
there.
a great place.
And you've spoken to us also about obviously the driving.
Well,
you weren't out there driving on your own randomly through the roads of Alaska, right?
He will, for an extra fee, he'll come down to your hotel and pick you up and then drive you the 19 miles or something up, and then 19, 20 miles home again. And I thought, I don't know. I mean, this is like, knowing roads I don't know. There's snow everywhere. We had, on the way up to those hot springs, we saw 3 cars off the side of the road upside down, like that. That's not one of them.
Bill was not out taking pictures of overturned
No, I was not doing that, so we got a generic upside-down car shot.
You
and
can't park there.
Everybody was okay because, we didn't see anybody, so they'd all gotten out.
But yeah, Arctic regions, driving, so worth paying
And I
people.
figured those were locals. So if they do that, there's not a chance I'm going to try to drive. So we paid the extra fee, and it's just, that way you don't have to worry.
And this is part of what you got,
yes,
right?
these incredible folds in the sky and you can see stars behind them. Yeah. I'm not sure what that constellation is there, but and this green, by the way, is very, very vivid. As I think you pointed out, when you're looking with your eyes, our eyes are not, built to find, to see these colors. So it's still amazing, and it's still pretty breathtaking, but it's not as great as when you.
We'll talk about this a little bit afterwards.
Oh, you got that? Okay.
And this is
this is one of my favorites.
And you captured a little bit of color.
A little bit
well.
of red down there in that one fold, if you can see that.
Right in the center.
A little bit. So we did get a little. I think that was probably the low altitude red, probably, because it's at the bottom of all of this.
And you also mentioned how fast they move, right? So this is.
So let me change this one. All right.
Yep.
So this, first of all, this looks like a big giant bird with a beak and his mouth open, heading toward the ground. And it was an amazing shot. All sorts of reddish stuff on the side, all kinds of interesting activity in there. But what I want to point out is I put a timestamp on here. It points out that this was 1:21 a.m. And less than 2 minutes later, I was pointing the camera in the same direction. Oh, I didn't want to.
Oh, sorry. I wasn't sure if your clicker worked.
I was still building it up. So let me just do that again.
Let's go back.
That is.
Pretend you didn't see anything.
Yes. Less than 2 minutes later, that exact same view, I did, zoom in a little bit, but it turned into that. I don't know how it does that, but I was there, so I saw it happen, And so it's just incredible stuff. And you notice again, there's a little tiny bit of red at the bottom. Yeah. But that was my money shot. That's the one that I send out to everybody.
That's the kind of, I think if you go aurora chasing and you get this, you're pretty happy.
Yeah, that would have been enough all by itself, I think.
And yes, they do move very quickly. Now, I've been going to Iceland usually. I go to Iceland for a couple of reasons. It was closer to where I was living before when I was back home in Europe. But there's a couple of other reasons why it's pretty nice to go to Iceland. It has lots of connections to planetary science, believe it or not. The Apollo astronauts trained there. Oh, wow. You might recognize this woman from seeing her quite a lot these days. This is Christina Koch. Christina Koch. She is one of the Artemis astronauts, and believe it or not, they also trained in Iceland. So these very unique landscapes that you have can be a little bit similar to the moon, and that is part of why they train there. Now, another great thing about going to Iceland, and I think the first feedback or the first thing you told us when you got back from Alaska was, oh my gosh, it was so hard to press the
painful.
camera button.
Like
and
20 below zero.
right. So when you are in Iceland, you get to benefit from this wonderful Gulf Stream, right? So this is this current of warmer air that makes the temperatures there a tad warmer than they should be at these latitudes. But do not get me wrong, it is also very cold occasionally down there, especially when you're in the north part. So brace for the cold, and occasionally you get to see other things when you're in Iceland that, forgive me, Alaska doesn't have.
No, I know.
So you get to catch volcanic eruptions. So last year, I got to catch both auroras and volcanic eruptions.
Well, I'll fight back on that a little. Alaska has volcanoes. They're just not quite as
just
good
angry.
to go watch. They're angry. They explode.
They're a little quieter. That's
Yeah,
true.
you don't get a
That
nice
is true.
gentle lava flow. You'll get a pyroclastic flow
Yep.
and an explosion. But
That's
anyway,
true.
point
That is
taken.
true. That is
Point
true.
taken,
Yeah.
though.
Iceland has been going through a very active period right now with its volcanoes. So they had this April Fool's eruption last year, right during chase season, which was pretty nice. Now, I want to briefly share with you some of the important aspects, which you already touched upon, and that is optics, right? So this image right here, it's an image from about 10, 12 years ago, and that was the first time I saw them. Now, yes, there are some clouds. You can see a little bit of that green right behind there, but believe it or not, I didn't actually see them. So I got back to my hotel, took a couple pictures of these beautiful mountains, came back, popped in my memory card to download the photos, and looked, and I thought, what? The auroras are there. How did I not see this?
Yeah.
And cameras have much stronger sensors than our eyes, right? So you might sometimes capture them and you don't even notice anything. And this is to give you an example.
Oh, wow.
So this is an image I shot last year, and to the naked eye, this was getting a little brighter, but when it started appearing, this is roughly what it would have looked like to the naked eye. So sometimes they can be confused with little clouds, little diffuse clouds, especially when they're just in a kind of a little arc or a little row. So you do want to preserve your night vision actually for them, and you want to look closely at what's up in the sky. And I thought this image was nice of you in front of the auroras because it really showed that kind of milky greenish color that you get at the start. But I do want to tell you, they are occasionally very, very bright and colorful as well, right? And the reason for this is that our night vision is largely black and white. Sometimes you don't notice this until I mention to people, and you're going to go home tonight, maybe you'll fumble around in the darkness for something, and you'll think, oh yeah, I'm seeing in black and white now, because you're using a different part of your eyes to see in low luminosity. We have rods or we have cones, and that's part of why occasionally if you're out at night and you're trying to, for example, see the Andromeda Galaxy, you need to look at it from your peripheral vision. That makes it a little easier. So that's part of the interesting ways in which our eyes work. And they'll also vary in intensity depending on where you're looking. So this is shot with a fisheye, by the way, so it's a really, really large angle. And you can see one section of the sky was very bright, whereas another one was diffused. But as you mentioned, they change really, really quickly sometimes. So it's worth sticking around, staying out there to have a look. And next, of course, people ask this all the time, you do have some photo editing. I have never revealed these raw images before. So this is the image that I shot, and this is what it looked like, the raw image, right? So this was kind of the start of it. So there was a little color visible to the naked eye, but it grew in intensity. But to the eye, it looked a little closer to this. And again, you want to adapt your night vision. So what are some elements to help you plan the aurora chase other than getting really good gloves and really good cold gear?
Layers.
So number one, very important, you can't see them in the daylight and you can't see them in the summertime, right? And this is a little bit of an illustration of why. You can see that aurora oval. This is from a forecast from just a couple days ago. And you can see that shadow. That's the night portion of Earth, because keep in mind, we are tilted as we rotate around the sun. So when we are pointed at the sun, when the northern hemisphere is pointed at the sun, the North Pole, we don't have nighttime at those Arctic latitudes. No night.
The land of the midnight sun.
Land of the midnight sun. So no auroras. But there is a time of year that is actually favorable. And you can see it on this graph. It's a little simplified, but you can clearly see March and April, September, October. And there's a very good reason why those months in particular are like this, and it is that we have the equinox around that time, right? So people celebrate the equinox, different parts of the world, start of spring, start of autumn, and it has to do with, again, where our tilt is in comparison to the sun, and there is an actual effect that is called the Russell-McFerrin effect. So the relationship between the interplanetary magnetic field and the Earth's magnetic field is optimized due to the tilt of our axis, how we are pointed towards the sun. It's still being investigated, the exact relationship, but it was discovered in the 70s, and it's been statistically verified, and that is when I usually chase. You also want to be a night owl. Coffee, very important. Occasionally you will get to stay in hotels and places like that have a little list like this. You can sign up, and the hotels will call you, wake you up in the middle of the night. I wonder if they ever have groggy, angry people. Oh, the auroras. Okay, great. So they have watchers who are out there checking for you so that you don't have to stay up all night, which is kind of nice. I've never had that, and I didn't have any on that night, but you know, it'd be nice to have them. Most of the time when you are going to see the lights, going to be about 10 p.m. to 2 a.m. because that is the darkest part of the night. You also need some weather apps, very important. Maybe don't rely on the basic phone one. So this is one that shows the cloud layers in Iceland. You want to check because sometimes it might show that it's socked in, but they're actually very thin upper clouds that will still allow you to see them. So very useful. I can tell you that one was an adventure to find some little holes in there to try and find it. And there's a couple of really good websites as well and applications. So this is emeraldskies.is, and it will tell you as it is happening live, which is really, really useful so that you don't have to stay outside in the cold necessarily the whole time. So hotels sometimes will actually have them just on a large screen TV. And this is one of my favorite applications. We actually use similar kinds of apps in the storm chasing community. So this is called Hello Aurora, and Hello Aurora allows you to make a report on there. So you're outside, you're in Alaska, you see the lights, you've taken your pictures, you go on the app and you put a little report, and that will help other people understand that the lights are out, that they're happening, and to look out for them. So it's a very useful tool, and it's available all over the world.
I wish
so,
I'd known about that.
I only discovered it a couple of years ago. Now, I want to warn you because there are lots of things that look like the aurora, not the aurora. The first years I was chasing, I kept seeing glow on the horizon from greenhouses in Iceland. Oh, no, it's not the aurora. So we'd get very excited. There's also what you're seeing on this picture, which is a very extreme example of it, is actually air glow. So it's pretty common, but it forms very differently, and it's constant. It's basically powered by stored UV radiation in our atmosphere, and usually it's invisible to the naked eye, but you will often get it on images. You also have something called SAR arcs. This is also a aurora. So it's associated, but it's...
call that a no-rora?
Yes, thank you for laughing. No one else got it. It is heat leaking in the upper atmosphere or the plasmasphere from this ring current, and essentially you're looking at oxygen being cooked. It is not visible to the naked eye, but it will show up on your images. It is a cool thing to capture, though. So, and here's one of my new discoveries is that you can chase from airplanes, believe it or not. So I've caught them now about 3 times in the past year and a half. And this is a very fortunate recent flight where they turned down the lights in the cabin. And that's going to be very helpful if you're trying to take images. Otherwise, you're going to need to shelter underneath some cloth or some coats or things like that because you're going to have too much reflection in the airplane windows from all the ambient light to be able to take pictures of them. And it was a pretty amazing show to see that from up there and to be really right up and close to it. Sometimes you're right underneath them. And I will give you the little tip. You want to fly kind of around. I will always see them in that region. So if you're flying to Europe, for example, right in between Canada and Greenland, if you're passing around there late at night, you will often see them. So look out the window, look for those kind of little white diffuse clouds, and those are often the auroras. Now, at certain times of year, and if you looked at the news in recent years, we covered it on AllSpace quite a few times, right? Auroras in the United States, auroras in New York, auroras in Texas. So it has been possible at times to see the auroras much further south. And this, what you're seeing is that auroral oval, I know it's red on here, and absolutely hugely expanding. You can see it's almost touching the north of California, and the auroras were actually visible in Los Angeles. I think we showed this 2 years ago. I shot this from Mount Wilson Observatory, or right next to it, and this was that glow on the horizon, a very rare magenta aurora, which we don't see very often. I do have to warn you, because it does pop up on the news now, don't all rush up to Mount Wilson. It is maybe once a decade, something like that, maybe once or twice. But the good news is we just had a very important launch of a space mission on Monday. So the SMILE mission was launched from Kourou in New Guyana. And it is a mission by the European Space Agency collaborating with China. And it stands, so SMILE stands for Solar, Wind, Magnetosphere, Ionosphere, Link Explorer. Sorry, slightly long name. But it's actually a dedicated, more or less, aurora mission. It's going to observe the solar wind interaction with the magnetosphere and the aurora oval. So it's still setting into place. So we'll talk about it again, I think, right?
Once we get some results from it, we'll definitely give some results from SMILE. We'll have a SMILE with SMILE. That'll be great. Well, thank you for that report on aurora chasing and how to go do it. And we did it now because you can plan to go in the fall. The fall equinox is a great time to aurora chase. So plan it now if you want to go on a chase. Go out there, do it.
And be prepared for potential disappointment.
Yeah.
I actually missed them this year. I went for 10 days, didn't see a single one. And that is the nature of chasing any phenomena.
Was that clouds primarily?
That's why we were showing you the hot springs and the other stuff to do, because you can plan to do other things while you're there. So.
Exactly.
Well, we're going to end with another short little mini feature here tonight, and then end with our multi-wavelength story. The NASA launched a mission called Spherex, and I was a little confused by this at first. I saw this and thought, well, this has an X at the end. It's an X-ray mission, and those nested, I thought they were mirrors. Well, look, this is Chandra. This is an X-ray, and those hoops you're seeing are actually the mirrors that send the particles down into the detector. They sort of have a grazing interaction with the particles because they're such hard particles. They're X-rays. So you need to have very gentle mirrors that can send it in there. And I thought that's what it was. I was completely wrong. Turns out they're actually photon shields. Those are there to block the light from external sources to keep the detector cold. When you're measuring in the infrared, this is an infrared telescope. The X has nothing to do with the wavelength. The X is actually the Explorer mission. NASA has a whole class of missions that are lightweight, easy, launch quickly, cheaper to go. They put an X on the back end of them because, well, it's just popular and sounds cool is my thought. But anyway, I was a little confused by it, but the result from this is amazing. Spherex observes in the infrared part of the spectrum. And what it looked at, well, it maps the whole sky. So it's just mapping the sky in infrared. It whips around, taking observation after observation. Well, it was looking at a region in Cygnus, the constellation, the Swan, the Northern Cross is another name for it. And it's the Cygnus X region of that. It's a star complex in Cygnus. It's about 4,600 light years away, contains the largest number of massive protostars in the Milky Way that we know of, at least, and has large stellar associations, the largest association with stars within about 2 kiloparsecs of the sun. Not to be confused with Cygnus X1, which is an X-ray source, which is, I think, why I was confused initially about all of this. That's about 7,000 light years away, and it's a binary system of a black hole and a hot young blue supergiant star. And the two are interacting, the supergiant's dumping material into the black hole, and that causes it to glow in X-rays. It also made the band Rush release an album or a song called Cygnus X1 for the fans out there. Again, epic, totally epic track.
Good stuff.
Good stuff. Anyway, back to the main thing. So it's not about the black hole. This was observing inside that green rectangle there, the star region. And you can see here is Cygnus on the left, the map, and sort of where the X crosses at Satyr there, the star, and Cygnus OB2, that's where these observations were taken. And Spherex observed here sort of with medium wavelengths. This was with the Spitzer Space Telescope, so this isn't Spherex yet. This is an older image of it. You can see the glowing gas, the glowing dust that's in there. Well, this is the Spherex image, and they took it in some shorter wavelengths such that the dust blocks out the light behind. You can see those dark lanes. You can peer through it a little bit, but not too well. Lots of stars in there, lots of young stars. Now, they decided, how can we peer through those darker dust lanes? Use a longer wavelength. So they use a longer wavelength, and this is what you see. All those blue features correspond to ice. It turns out that they've tuned this instrument to be able to pick up ices in these very cold regions, in these star-forming places. And yes, that's what these are. It's seen in 3 micron and 3.3 micron for those that are keeping track, keeping score out there. But what it was water ice and CO2 ice in these regions. So pretty darn cool that we're mapping ices in cold outer space regions where stars are forming. And this tells us that the universe has the building blocks for things like comets and cold icy objects that are out there. They could be swept up and turned into dwarf planets and all sorts of things. So a cool result from Spherex. It's going to continue to observe the heavens and do its all sky spectral survey. So you're going to probably hear more from Spherex as time goes on. We're going to do a few pretty pictures here. This is the moon taken by David Pinsky. Thank you, David. We always want to include a Pinsky photo when we can. He's a staff member here. And then Laura May, you found some interesting shots of our camera obscura, rather.
Right. Both showing the sun. So we have this beautiful pinhole camera. You might have visited it upstairs. It actually would have just shut. And you can actually see the sunset at a specific time of year. It's usually between, I think, about April to August. So this is a recent image of the sunset. And you can see lots of people come in and join. It is an instrument, right? So it is projecting that beautiful sunset. So I highly encourage you to come up one of these days. Sunset is around 7:40 right now, 7:45, and experience it for yourself. You've got a couple other months. Come on a day that's not cloudy, obviously, and you get to see this beautiful, incredible sunset without damaging your eyes. And sometimes we see the green flash as well.
Very cool.
Now, this is an image that I shot during a recent tornado chase, and that is Jupiter, that little dot right in that little corner there on the right. And Jupiter pictured with another form of Jupiter, mythological Jupiter, god of lightning. And so this was an exciting shot to get both lightning and Jupiter together.
Very
Jupiter
cool.
and Jupiter.
Very cool. Well, Ginger will return next month, and we'll do an expanded, a longer, beautiful astronomical photos. So amateur astronomers, send us your images.
Please.
We'd love to include them. Well, I want to talk until the end of the show about astronomers using wavelengths to observe things. This is the visible light spectrum. We're all familiar with this. This is what our eyes pick up. And for long periods of time, we observed with just our naked eyes. We made maps. Then we made instruments that could gather light. Well, then we eventually discovered that there are other kinds of radiation. This is our exhibit here called Beyond the Visible. And it includes wavelengths that are both shorter and longer than visible light. It covers gamma rays, X-rays, ultraviolet, visible, infrared, submillimeter, and microwave submillimeter, and then finally radio waves are the longest. So I'm going to talk a little bit briefly, and you can see here are their wavelengths. They cover a vast range from things that are tiny, tiny, less than 10 picometers, all the way up to things that are literally dozens of meters long. So very, very long wavelengths. Now, we've built different telescopes to observe all of these. Space telescopes for the short wavelengths that can't make it through our atmosphere. Of course, Hubble, Galaxy is an X-ray telescope. Webb is observing infrared. Water in our atmosphere absorbs a lot of the infrared radiation, so you can't observe from the ground in all the wavelengths of infrared, so we launch them to space. The Planck satellite was doing microwave range, and of course radio dishes here on Earth, although we have some submillimeter dishes on Earth as well. We tend to put them up high up, get above as much of the atmosphere as you can. Well, I want to talk a little bit about how things change as you take pictures. This is the same galaxy taken in different wavelengths. On the left are the X-rays. Those tend to pick up the most energetic events, things like black holes eating gas, an active galactic nucleus, the core of a galaxy that's shredding stars will cause X-rays to glow. Ultraviolet is usually associated with star formation, where you have lots of stars forming. They can give off lots of UV and glow. So you can see how it's tracking the spiral arms in M51 where the stars form. Then in the visible light, you're seeing all the glowing stars that have been living their lives, the old ones, the dying ones, the young ones. You see all of it in the glowing gas. Infrared, depending on where you've tuned it, you can either see glowing gas or you can peer through the gas and see the objects behind. So infrared gives you a lot of possibilities and a big lever arm. Millimeter is interesting. You start to be able to probe into the range of molecules. You start to be able to look at things like carbon monoxide and carbon dioxide and water molecules, and interesting transitions in molecules you can measure in these. So it opens up a whole new ability. And also, you can get really, really great resolution because we can do what's called aperture synthesis. You can use multiple dishes, combine them together. And that's what they do with ALMA in the Southern Hemisphere. In fact, I want to talk about a result that ALMA helped with. This is the interstellar comet 3I Atlas. And it came in through our solar system from another star. And as it passed through, we observed it with Hubble. This is a Hubble Space Telescope image in the visible, but astronomers fairly recently observed it with ALMA in the submillimeter. And they detected methanol around the comet. So the methanol, we didn't know about it if we had used the visible light. We had to use our submillimeter telescope in order to pick that up. So by using both, we could detect it in the visible, use another instrument, and measure these aliens. Okay, it's not an alien spacecraft, but they were drinking methanol, whatever they were doing.
It's a drunk comet.
It's a drunk comet, exactly. Although I don't think methanol is the kind you can drink.
No, probably
Be safe
not.
out there, people.
Yeah,
Check with your doctor.
Don't do this at home.
You could use it as a rocket propeller.
Yeah, we could. Another one that was done was a fast radio burst result. And I know, Bill, you're a big fan of this, but we're running out of time, so we can't chat too much about it. But you've been finding stories about these for a long time, and they're very brief bursts of radio waves that contain huge amounts of energy. And discovered in 2007 when astronomers analyzed archival data from the Parkes Observatory in Australia. Well, the radio waves travel to us. It turns out that the blue reaches us first. Well, blue, none of the radio waves are blue, but the shorter wavelength blue radio waves get to us first. The longer ones take a little longer, and it's actually due to electrons along the path actually slow down the longer wavelengths. It'll also change the polarization, but we don't have time for that. But we can measure that, and we see this happening. We see the short wavelengths hit first with these fast radio bursts, then the longer. But we've never been able to observe them in multiple wavelengths. They kind of happen randomly. There's one that repeats, or two now that we found that repeat, but most of them are sort of in random directions. Well, there was one observed where the Swift telescope and Fermi picked it up. Both of those have capabilities that they can see large portions of the sky at once. So they're able to observe. Now, Swift is meant to find things like a burst in gamma rays, and then it can go and pinpoint where those are. And the same with Fermi. They're looking for gamma ray bursts. Well, they were observing the sky, and it turns out they picked this up at the same time that the CHIME telescope picked up a fast radio burst. And they were able to measure both in gamma rays and in the radio waves that this object gave it off at the same time, and confirm that this happened in a magnetar, a highly magnetized neutron star that was, anyway, a highly magnetized neutron star that had a flare, and the flare gave off gamma rays and radio waves. So we're learning about these fast radio bursts because of that. Another observation that dealt with Hubble and Chandra, Chandra's in X-rays, Hubble's invisible, are these little red dots. Maybe you've heard of them. On the James Webb Space Telescope has been observing these little faint red things on the far side of the universe. Well, we observed one that flashed in X-rays. It's glowing in X-rays. We were hoping we'd find this, by the way. If these little red dots are black holes and materials falling into them, they should have X-rays. Most of them do not. This is the first we've seen that had X-rays, so we can observe it in both these wavelengths and try and figure out what these things are. This is a little bit of a preview, folks. In July, we have an expert from Penn State coming. Dr. Leha is going to come and tell us about these little red dots, so hopefully we'll learn all about them.
And we even observed the sun, of course, in different wavelengths. Some of you might remember these stamps that were actually put out by the U.S. Post Office, these forever stamps, and they actually show these different features that we get to observe on the sun. Of course, some of you may be familiar with the H-alpha, hydrogen alpha. You can actually observe this upstairs also through our coelostat. That's where we see the upper chromosphere. So we're going to see flares, those eruptions, filaments and prominences. You can see them on the outside here. And you can come see them any single day, every single day at the observatory when it's not cloudy.
We need to go through this pretty quickly, though.
That's right. So. And we also have calcium K that we can observe different structures on as well, the magnetic skeleton of the sun that you can see. So you can see a comparison here of these sunspots. And of course, we've got solar flares that we get to see in all of these different wavelengths. But we can even observe this in radio. This is the ALMA telescope. Again, observing in the daytime. You can see the sun up there. And this is what it looks like in radio. And so this will show us different features on the sun. And here's a sunspot region in radio. Pretty exciting. You get to see also these temperature differences.
Yeah, so the sun, you can image it in radio. It just doesn't have radio bursts like I was talking about. Now, in addition to using other wavelengths like X-rays and radio waves, we are now using particles and gravitational waves to study the universe. This is Super Kamiokande in Japan. It's a detector that can see cosmic rays as they, neutrinos as they come in. And Kamiokande 1, the earlier one, found neutrinos coming in, and actually it saw supernova 1987A. Supernovae, when they explode, give off neutrinos. They saw a burst of neutrinos about 18 hours before the visible light happened. That's expected. The neutrinos are created when the explosion happens. They fly through the star, they reach us very quickly, they travel nearly the speed of light. That shock wave takes time to travel through the star, and we think it would take 18 hours or so to reach the surface before the visible light would break out. So we expected that delay, and we measured it. It was very cool. In addition, we've seen the sun sort of in neutrinos, Super Kamiokande. They can measure the direction the neutrinos came from, and they can backtrack it, and it turns out these all came from the direction of the sun. So neutrinos, radio, IR, X-ray, UV, and visible. We have the sun in all of those, which is cool. We even have the shadow of the sun, which is a great Zen Gorilla album, I just realized. Anyway, this is another detector, Ice Cube, up at the South Pole, Antarctica. They buried detectors down in the ice. Well, these cosmic rays coming in from the southern, below the Earth actually, so I guess from the northern hemisphere, shooting through the Earth, going down into there. Well, they were watching this and the sun was in the way. Well, it blocked some of these particles coming in, these cosmic ray particles that they're detecting. Well, they were blocked by the sun. So you're seeing on the right hand the shadow of the sun in cosmic rays, actually. So we're able to sort of not detect the sun in a weird way there. Another thing we're using is gravitational waves. LIGO, it's an observatory that measures literally the fabric of the universe shaking when things like black holes merge. We've seen lots of these. We've had guests here to talk about it. And then we have multiple of these detectors so we can verify that they're real. Well, one of the most interesting things they found was colliding neutron stars. And this happened quite a long time ago. And I'm going to run the video of it here and talk over it. So 2 neutron stars were spiraling around one another. And as they do so, they sort of shake the fabric of space. You can see those wiggles happening. And that gives off energy, which makes them lose energy. And they spiral in and merge. And when they do, you end up getting what's called a kilonova. And in that burst, you make gold and platinum and silver. You make most of the bling that people love. Now, when that happened, the LIGO gravitational wave detectors found it, and they were able to triangulate and say, hey, it's over in that direction. Well, ground-based telescopes were able to slew over in that direction, start taking images, and they found the afterglow. And it was through the spectroscopy of the afterglow they were able to see all these elements get created in colliding neutron stars. So this is our new periodic table. We're able to say Big Bang fusion makes hydrogen and helium and a little bit of lithium. Cosmic ray fission makes beryllium and a little bit of lithium, and I don't think technetium is. That's something else. No, technetium is cosmic ray fission. Anyway, merging neutron stars, that's that orangey color. All the ones that have some orange in it are made in those merging neutron stars. Exploding massive stars make the other. So astronomers, we've really pieced together where the elements are created in the universe and how they're made. And this is a friend of mine, Jennifer Johnson, astronomer that was in graduate school with me, created this after that story about the colliding neutron stars. Now, we have seen more colliding neutron stars happen, but we have not picked up the gravitational waves from them. So we haven't had that pairing again yet. So we're waiting for that. But astronomy isn't just about visible light. We use a lot of different wavelengths to piece together what's happening in the universe. And now we're using particles, and we're also using gravitational waves to learn. Gravitational waves are especially interesting because we might someday be able to peer past the cosmic microwave background radiation, that wall that we can't see past. That gravitational waves go right through that. So anyway, we're looking to have a cosmologist come to us soon. When we have that verified, we'll announce it, but maybe in September, and we can ask about that. Well, that's our show for tonight, folks. We hope you've enjoyed All Space Considered tonight. Thank you so much. Yeah, I want to thank our panel. Thank you so much, everybody. Really appreciate you joining me tonight. Thank you, Laura May, for being my co-host as always. All Space Considered is brought to you by Griffith Observatory, the Department of Recreation and Parks of the City of Los Angeles. And as always, we thank Griffith Observatory Foundation, our exclusive nonprofit partner. And we will see you next month. We are going to come to you from the Convention Center in Pasadena, where the American Astronomical Society meeting is happening. We're going to record our show there live, and we'll still broadcast it on Thursday. So you can watch it on YouTube, and we'll see whether we show it in the theater on Thursday night for you. I'll talk to Mark about that. You might be able to come up and watch it on the screen. But look for that. It's going to be a fun show. We'll have some astronomers right at our fingertips. Who knows who we'll interview? But we're looking forward to having an interesting show next month. Again, thank you for joining us, everybody. We'll see you next month.
Thank you.